স্টুডেন্ট অফ ক্লাস 8, আমি আজকে তোমাদের এই পরিবেশ ও বিজ্ঞান এনভায়রনমেন্ট অ্যান্ড সায়েন্স এই চ্যাপ্টারের যেটা পড়াবো সেটা হচ্ছে ঘনত্ব ও চাপ। ঘনত্ব ও চাপ। ডেন্সিটি অ্যান্ড প্রেশার, সেটা হচ্ছে যে ঘনত্ব কাকে বলে। হোয়াট ডু ইউ মিন বাই ডেন্সিটি? ডেন্সিটি হলো প্রতি একক আয়তনের ভর, তাকেই বলা হচ্ছে ডেন্সিটি বা ঘনত্ব। তো আমরা যদি ডেন্সিটিকে ডি দিয়ে মেজার করি বা ডি দিয়ে ডিনোট করি, তাহলে ডেন্সিটি ইকুয়ালস টু মাস বাই ভলিউম বা এম বাই ভি। সেক্ষেত্রে এম দিয়ে আমরা মাসকে ডিনোট করছি এবং ভি দিয়ে আমরা ভলিউমকে ডিনোট করছি। সো দ্য ফর্মুলা ইজ ডি ইকুয়ালস টু এম বাই ভি। Density is the property of matter. Density is the property of matter, and density unit হচ্ছে CGS unit gram per centimeter cube or gram per cc or gram centimeter to the power -3, আর SI unit হচ্ছে kilogram per meter cube or kilogram meter to the power -3. So this is for CGS system and this is of SI system. তো এর জন্য কতগুলো জিনিস একটু আলোচনা করার দরকার আছে। যেরকম তোমায় যদি বলা হয় 1 লিটার ওয়াটার, 1 লিটার ওয়াটার বা 1 L ওয়াটার, তাহলে সেক্ষেত্রে আমি লিখতে পারি 1000 সেন্টিমিটার কিউব ওয়াটার। তাহলে 1 কিলোগ্রাম ওয়াটার ইকুয়ালস টু 1000 গ্রাম ওয়াটার। তার মানে এটা লেখা যায় যে 1000 সেন্টিমিটার কিউব ওয়াটারের mass of water is 1000 gram. Therefore 1 centimeter cube mass of water equals to 1000 divided by 1000. So we have 1. Therefore 1 gram per centimeter cube. So this is the density of water in CGS system. So the density of water in CGS system is 1 gram per centimeter cube or 1 gram per cc. Now if you want to convert it in SI system, what is the process or what is the value of it? First of all, we have to convert. Our main target is to reach kilogram per meter cube unit. If we want to express the density of water in SI system, we have to convert it in kg per meter cube unit. So first of all, we have to we know that 1 gram per centimeter cube is the density of water in CGS system. So if 1 kilogram equals to 1000 gram, then 1 gram equals to 10 to the power -3 kilogram. And we know that 1 meter equals to 100 centimeter. Therefore 1 centimeter equals to 10 to the power -2 meter. Therefore we can write it down. 1 gram equals to 10 to the power -3 kilogram divided by centimeter cube. That means 1 centimeter into 1 centimeter into 1 centimeter. So we can write 10 to the power -2 whole to the power 3 meter cube. So what we have, that is 10 to the power -3 divided by 10 to the power -6 kilogram per meter cube. So that will go up and it is converted into 10 to the power 3 kg per meter cube or 1000 kilogram per meter cube. So the density of water in CGS system is 1 gram per centimeter cube, and the density of water in SI system, it is 1000 kilogram per meter cube. Okay. Now what is the density of mercury? You know mercury is heavier than water, and mercury is a liquid. So this is the exceptional liquid whose density is higher than water, and the density of mercury is 13.6 gram per centimeter cube or cc. Okay. Therefore, we are going to the next part of this book, that is pressure, the pressure of water. Actually, whatever we have discussed now, that is about the density of liquid, especially the density of water, and the density of water in CGS system and SI system, that we have discussed. And we have mentioned that the density of mercury is 13.6 gram per centimeter cube. It is for your information that you have to remember. Okay, sometimes the short question will come asking you the density of mercury. Now we are going to the pressure of liquid. We are removing both the content of the boat. Okay, so the pressure of liquid. Pressure of liquid is actually, when we have studied in classroom, then we have studied in a with so many explanations and so many examples. But as it is a revision class, and you know about the examples and explanations, so I am going straight to the point where the formula of pressure of liquid is given. Suppose this is a beaker, and very easy example of liquid is water, and it is kept. Okay. We want to find out the pressure at this point, and the point is, say for example, O. So we have to find out the pressure at that point O, at the point O. We consider that point is at depth h from the open surface of the water. So we consider one imaginary circle keeping O at the center of this circle, and we consider the area of that circle is A. Now we imagine one cylinder. So the height of that cylinder is h and the cross-sectional area is A. Now what is the mass of that water cylinder? Mass equals to, I'm sorry, actually we are not going to measure directly mass, the volume of the water cylinder is cross-sectional area into height. So A into H is the volume of that water cylinder that we have imagined. Okay. Now what is the mass of that water cylinder? We can use some density. It may be d, small d. So density of that liquid is d. We consider it. Now what is the mass of that water cylinder? Mass of the water cylinder is mass into volume, that is density into volume equals to mass. So we have the volume is AH into density D. So what we have, AHD is the mass of that imaginary water cylinder what we have imagined right now. Now, what is the weight of that water cylinder? What is the weight? We have to find out the weight of that water cylinder what we have drawn over here. So the weight of the water cylinder is simply mass into gravitational acceleration, that is g. So AHDG is the weight of that imaginary water cylinder which is giving pressure at the bottom of that imaginary water cylinder, and this point is not actually at the bottom of the beaker, it is within any place of that water. Actually it may be any point, or it may be the extreme bottom of that beaker also, but for calculation, for the deduction, mathematical deduction, we consider that point O is actually within this liquid, from the open surface of that liquid to the bottom of that beaker, and the open surface, from the open surface to the point at which the imaginary water cylinder is giving pressure or giving weight is h. So it can be set the depth of that point from the open surface of the water. Now, what is the force or what is the weight is actually applied by that imaginary water cylinder to the point O is AHDG. Now, what is the pressure? As you know, the pressure equals to force. It may be modified, the normal force divided by area. So the force is AHDG divided by area is A. So we have HDG. So pressure P equals to H into D into G. This is very important formula for finding out the pressure of any liquid at any point inside that liquid. So what we need to find out to measure the pressure under the liquid, first of all, the point at which the pressure I have to measure, that point, what is the depth of that point from the open surface of that liquid, whatever liquid I am given to find out the pressure. Secondly, I need the density of that liquid. If it is water, then you know the value of density of pure water in CGS system and in SI system. You know it. In CGS system it is 1 gram per cc, and for SI system it is 1000 kilogram per meter cube. If it is not water, if it is some other liquid, then you have to know the density of that liquid, and density of that liquid can be easily we are getting from any source, from me also, from Google, from anywhere. You are getting the value of density of that liquid. And G with the gravitational acceleration, we know the value of gravitational acceleration, that is 981 centimeter per second square or 9.81 meter per second square. Okay, so in which system you were measuring the pressure of that liquid, you have to just maintain that system. You have to maintain it by in centimeter. If you were deducting in CGS system, you have to maintain it in CGS system gram per centimeter cube, and also this is per centimeter per second square if you were finding out the value of pressure in CGS system. If you are finding out the value of SI system, then the height will be measured in meter and D will be measured in kilogram per meter cube, and G will be measured in meter per second square. That's how we can find out the pressure of liquid at any point inside the liquid. One thing is important, that is the point should be situated inside the liquid. Okay. Now we are going to give one example. One example is very simple example that you have in your textbook, that you were given a bottle you are given a bottle, okay, and the water is kept up to that level. You have made some holes here at the middle, at the bottom. So you have made some holes. It may be a plastic bottle, it may be, actually plastic bottle is easier because glass bottle you can't make some holes like that easily, and it should not be experimented by you because it will bring hazards. So I suggest you take plastic bottle, the uh, plastic bottle what is kept in your house at scraps. You put some water in it, and before putting some water in it you make three holes at the different height, one hole at the bottom, another hole at the middle, and the last hole, the uppermost hole at the neck, just below the neck of that bottle. Then you give some water into it. Some water, that means I want to say the bottle should be filled completely with water, and it should be kept on a tabletop or some higher position where the floor is not very close to that bottle. Then you can find that the upper holes, the water are getting out from upper holes, and it is dropping, it is falling very close to that bottle. After that, the second one, the water is going little bit away, but the last one actually give you more distance, and the reason behind that is actually the pressure. At this point the pressure is actually, this is the depth H1. If we consider this is the depth H2, and another depth if we consider this is H3. So it is very clear that H3 is greater than H2 is greater than H1, and as H dg we have the gravitational acceleration cannot be changed. Density of that liquid, whatever liquid you were actually using inside that bottle, basically we are using water because it is easy available, it is not dangerous chemical compound for our skin and for our usage, and it is basically you can't purchase this liquid from outside. So this experiment is very easy experiment, and um, through this experiment what we can actually, what I am saying, that density of that liquid or water is not changing, g gravitational acceleration, that will not change. So what is actually changing, that is the height. Whatever holes you have made on the bottles, they have different depths. So here as the H1 is less, so the pressure will be exerted less, and H2 is greater than H1, that's why the pressure exerted at that point will be more than the point that of H1. And again the depth H3 is much greater than H2 and H1, it will exert more and more pressure, and that's why the water is moving far away from the bottle. Okay, this experiment proves that the pressure of water increases with the depth, or I just want to generalize the statement that any liquid, it will exert more pressure according to increasing of its depth. Okay, it is simple. And more one thing I am going to explain, that is also important, that take another bottle. Actually when you are using these plastic bottles and make some holes on it, it is basically useless. After doing this experiment you have to throw it out, or you have to keep for further experiment, same experiment if you want to exhibit, you want to show your parents, your sister, your brother, whatever be. But you have to take another plastic bottles and you make two holes at the same depth. At the same depth you make two holes and you pour some water in it, and what you can see, the water is moving out from these holes. They are equally forced. The force is equal. Okay. So through this experiment, what is proved? It is proved that at a certain depth the liquid pressure is same at a certain depth, because these 2 points are actually at the same depth h1, or it is h3, so h4, at the same depth, and that's why it is giving the same pressure of that liquid, and that's why it is moving with the same force. Okay, and it will go away from the bottles at the same distance, approximately same distance. So today is up to whatever I have studied now, whatever we have learned now. This is Thursday. Oh, this is Friday. Saturday. No, again we are meeting at our school at 27th of this